This recording is the second part of Module 14 in physics. And this part of the module is going to deal with capacitors. So when you bring charges together in one place, each of those charges is going to have its own electric field. And so the total electric field would be the sum of all those electric fields. But there are certain situations when you have something that is called a capacitor. And a capacitor is a device that stores charge. So this is in your textbook, but let's go ahead and draw a capacitor. And this type of capacitor is called a parallel plate capacitor. So what you have are two metal plates. So this is a metal plate. This is a metal plate. And one of these plates is lined with negative charges, and the other is lined with positive charges. And then you have a wire that allows you to attach this all to a circuit. And then the other important piece of information, which we'll discuss here in a little bit, is how far apart the plates are, and that's called the separation distance. So these plates have opposite charges, and because the charges are opposite, they are going to be attracted to each other, but they can't move because in a capacitor there is an insulator between them. So the charges stay there, but they are trying to get as close as possible to each other. So in a parallel plate capacitor, you have these positive and negative charges, and you can calculate the electric potential that a capacitor produces. And actually the electric field from all the individual charges add up. So it's relatively simple to calculate the electric field, or the electric potential. So the formula is that electric potential is equal to Q divided by CQ. And that's defined each of these. So V is the electric potential. Q is the amount of positive charge that is stored in the capacitor. And then this other variable, C sub Q, is the capacitance. So basically, what the electric potential is telling you is how much charge can a capacitor hold at a given voltage. So the larger the capacitance, the more charge it can hold. Now it's also dependent on other things because a bigger plate is going to store more charge. So the capacitance is going to be high. How far apart they are, so the charges, if they're really far apart, the charges aren't going to attract each other much, so capacitance is going to be low. Okay, so if we rearrange this equation that we have here to calculate the capacitance, then what we would get is that the capacitance is equal to Q divided by V. So if we look at the units that are involved here, so the unit for Q is in coulombs, and well, we know that the unit for electric field is a volt. So we have a coulomb over a volt, and that is called a farad. It's named after Michael Faraday. Now this is a pretty big unit, so often we will actually look in micro farads, but it's a coulomb over a volt. So what does it mean? Well, what the electric potential tells us is that, so if the electric potential equals 5 volts, so if V is equal to 5 volts, what that means is that the potential difference between those two plates would be 5 volts. Okay, that's what the electric potential is telling us. So a charge is any charge that is moving from one plate to the other plate would experience a change in electric potential of 5 volts. So in other words, these are fixed charges on the plate, but then if you place a freely moving charge starting at the positive plate and moving to the negative plate, if the electric potential is 5 volts, that means that it will experience a change of electric potential in an electric potential of 5 volts. Okay, so if a freely moving charge is moving from negative to positive, then we say that that indicates an increase in electrical potential. If the particle is moving from positive to negative, then we would say that represents a decrease in electrical potential. Okay, so a charge that is placed near the positive, so if this is the positive plate and this is the negative plate, a charge that is placed near the positive plate will accelerate toward the negative plate, and the electric potential is what determines how fast it will accelerate. So don't worry if that's a little bit confusing for now. Let's look at an example. So we will start with example 14.5. And that says that we have a 2.6 times 10 to the negative 6 farad capacitor, and that it is charged so that there is a 2.5 millicoulomb total charge, and we want to know what is the electric potential of that capacitor. Okay, so we know that the electric potential is equal to Q, the total charge, divided by the charge that is on the positive. So this 2.5 millicoulombs is the total charge that is on the positive plate. And then this would represent the charge of the capacitor. Okay, so this is just a simple matter of putting in the values. So it's the total charge on the positive plate, 2.5 times 10 to the negative 3 coulombs, divided by 2.6 times 10 to the negative 6 farads, which we already said is a coulomb over a volt. Okay, so the coulombs are going to cancel and you're going to be left with V, the electric potential. We know that the unit for electric potential is a volt. So if we do this math and with two significant figures, you should get 9.6 times 10 squared volts, or you could say 960 volts. Okay, so that's just a straightforward application of the electric potential formula, the total charge on the positive plate and the charge of the capacitor. Okay, so now let's go ahead and do on your own 14.8. Okay, so here we are given that the capacitor is 4.6 times 10 to the negative 6. So 4.6 times 10 to the negative 6 farads. Okay, so that is going to be the charge on the capacitor. And we are told that the electric potential is 125 volt. So a 125 volt electric potential And then we are asked what will be, how much charge must what must be stored. So we're looking for Q, the amount of charge that is stored on the positive plate. Okay, so V is equal to Q divided by the charge of the capacitance, and we want to solve for Q, so we'll just multiply both sides by this. Okay. Okay, so then it's just a matter of plugging in the numbers. So this would be 4.6 times 10 to the negative farads, and a farad is a coulomb per volt, and we will multiply that times the electric potential, which we saw was which we were given as 125 volts. Okay, so the volts are going to cancel, and we will get that Q is equal to 5.8 times 10 to the negative 4 coulombs. So this is the amount of charge that is stored on the positive plate. Okay, so then let's look at how capacitors can be applied. So you have this electric potential that is created between plates, and the electric potential means that means the difference between the positive and negative plate. So if a charge moves from one plate to another plate, it's going to experience a change in electric potential. And we already said that if it goes from negative to positive, that's going to be an increase in electric potential. And if it goes from positive to negative, that represents a decrease in electric potential. Okay, so capacitors are used to accelerate charged particles. So if you have a positive charge next to a positive plate, they're going to be repelled and they'll be attracted to the negative plate. But so it'll accelerate toward the negative plate. And it's the electric potential of the capacitor that determines how fast it will be going when it reaches the negative plate. So again, if we have a capacitor and we have positive charges on one plate and we have negative charges on the other plate, if we place a positive charge next to this positive plate, then it's going to be repelled by the positive plate, but it's going to be attracted to the negative plate. So it's going to accelerate towards that negative plate. And the electric potential V is what will determine how fast it will be going when it reaches this negative plate. And again, why is that important? Well, it's important because we know that moving particles means that you have kinetic energy, and that kinetic energy can be used to do work. So if you start with a with a stationary particle and then it moves, then you know that potential energy is going to change, right? And if potential energy is changing, then kinetic energy is also going to change. So the greater the change in electric potential, the greater the change in potential energy, and the greater the change in kinetic energy, which means the greater the change in speed. Okay, so let's look at example 14.6, and let's help this to make a little more sense. Example 14.6. So that example, we have a freely moving electron. So the mass of this electron is 9.1 times 10 to the negative 31 kilograms. So it's an electron, very small. That's its mass. And we are given that Q. Its charge is negative 1.6 times 10 to the negative 19 coulombs. And it starts at rest and travels from the negative plate. So it's starting at the negative plate. So it's going to be going negative to positive, which means that means that we're going to get an increase in electric potential. And we are told that the capacitor is 3.1 times 10 to the negative 6 Faraday. Okay, this is a capacitor. And then we are asked how fast will it be moving? And we are to assume that the capacitor has 0.55 megacoulombs of stored charge. Millicoulomb, did I say mega? Millicoulomb. So it's going to be 0.55 times 10 to the negative 3 coulombs. Okay, so where do we start on this? We need to look at the energy that is involved in the system. And in order to determine the speed, we need to know the kinetic energy. Okay, so you know that, so it's starting at rest, so there's going to be a change in potential energy. And we know that the change in potential energy is equal to Q delta V. And then we also know if the change in potential energy, what's it getting changed to? It's getting changed to kinetic energy. So then we could use kinetic energy is equal to 1/2 mv squared. Okay, so that means that the first thing we need to figure out is we need to figure out what is V. Okay, in order to get the potential energy, we need to figure out the change in electric potential. Okay, so let's start doing that then. So V is equal to Q divided by the capacitor. Okay, so V. Okay, so Q, capital this Q is the charge that is on the positive plate, and we are given that as this. Okay, so it's going to be 0.55 times 10 to the negative 3 coulombs, and this is the charge of the capacitor, so that's going to be 3.1 times 10 to the negative 6 Faradays. And remember, a Faraday is a Coulomb over a volt. So the coulombs are going to cancel, and you will be left with volts. So that V will be equal to, how did we do this? V is going to be equal to 1.8 times 10 squared volts. Okay, so now that we know V, then we can, we know that delta PE, delta, the change in potential energy, is equal to Q delta V. And we just calculated what that delta V is, and we're given Q. Okay, so the change in potential energy is equal to 1.6 times 10 to the negative 19 coulombs. And that's a negative number because it went from, it started at rest and traveled from the negative plate to the positive plate. And then the V that we calculated is equal to 1.8 times 10 squared volts. And let me remind you that a volt is a Newton meter. So this is a Newton meter over Coulomb. So the coulombs are going to cancel. You'll be left with Newton meter. So a volt is a Newton meter of a Coulomb. So over Coulomb. So the change in potential energy then comes out to be negative 2.9 times 10 to the negative 17 Newton meters, which is a joule. Okay, so we had a negative potential energy means that you have a decrease in potential energy. So if the potential energy decreases 2.9 times 10 to the 17, then that means that the kinetic energy had to increase that amount. So the kinetic energy is 2.9 times 10 to the 17 joules. Okay, so now we can use that number, and we know that kinetic energy is equal to 1/2 mv squared. So now we can solve for v squared. Go ahead and erase this. So kinetic energy divided by 1/2 m equals v squared. And if we take the square root of that, we'll get v. Okay, so the kinetic energy that we calculated was 2.9 I'm going to scoot all this over. So V is going to be equal to the square root of the kinetic energy divided by 1/2 m. Okay, so the kinetic energy that we calculated was 2.9 times 10 to the 17 10 to the negative 17 joules divided by 1/2 divided by the mass, 9.1 times 10 to the negative 31 kilograms. Okay, so just so we can see how the units work out here. So a joule is a Newton meter, and a Newton is a kilogram meter over seconds squared. Okay, so the kilograms are going to cancel. Kilograms are going to cancel, not the meter. Okay, so the kilogram will cancel. So you're going to have meter times meter, meters squared over seconds squared. When you take the square root of that, you end up with meters per second. So if we do all that math, you should get that the velocity is equal to 8.0 times 10 to the 6 meters per second. Okay, so that particle, that charge, that freely moving electron started at rest, traveled toward the negative plate, and traveled from the negative plate to the positive plate, and it would do that moving at a velocity of 8.0 times 10 to the 6 meters per second. Okay, so let's go ahead and do some on your own. So on your own, 14.9, just write down what we are given. So you have a proton. It's going to be a positively charged particle, and its mass is 1.67 times 10 to the negative 27 kilograms. And this is the proton. So it's a positively charged particle. And it is placed at the edge of a positive plate, and the capacitor is 3.4 times 10 to the negative 6 Farad. So this is the this is the capacitor. And then the capacitor holds 12 millicoulomb of charge. So that would be the charge on the positive plate. And so that would be 12 times 10 to the negative 3 coulombs. It's going to be equal to Q. And then how fast will the proton be moving when it reaches the negative plate? Okay, so this proton is going to be moving from positive to negative. So that means that we're going to get a decrease in the electric potential. Okay, so again, in order to get to velocity, we know that kinetic energy is equal to 1/2 mv squared. So we've got to get to kinetic energy in order to get there. And we can, to get there, we need to get to the potential energy. So we know that potential energy is equal to Q delta V. Okay, we were given the mass. We were given the charge, or this is a small q actually. We were given the stored charge. Okay, so we can calculate potential energy if we can calculate delta V. So delta V is going to be equal or just V. V is equal to Q over the charge of the capacitance. So that is going to be equal to 1.2 times 10 to the negative 3 coulombs divided by the CQ, which we are given, the capacitor, 3.4 times 10 to the negative 6 Faradays, which is coulombs over volts. Okay, so the coulombs are going to cancel, and so we get that V is equal to negative 3.5 times 10 cubed volts. And it's negative because it was traveling from the positive plate to the negative plate, so you're going to get a decrease in delta V, a decrease in the electric potential. Okay, so now that we know the electric potential, we know that the change in potential energy is equal to Q delta V. So the change in potential energy will be equal to 1.6 times 10 to the negative 19 coulombs which we were given, times the delta V, which would be negative 3.5 times 10 to the negative 3. That's the variable that we calculated. So I'm going to put in here that a volt is a Newton meter over a coulomb. So coulombs are going to cancel. You're going to be left with Newton meters, which is a joule. So the change in potential energy then is negative 5.6 times 10 to the negative 16 Newton meters or joules. Okay, so now that we know if the potential energy decreased by negative 5.6, then we know that the kinetic energy must be equal to, that had to get converted to kinetic energy. So kinetic energy is equal to 5.6 times 10 to the negative 16 Newton meters. Okay, and we know that kinetic energy is equal to 1/2 mv squared. So kinetic energy divided by 1/2 m, and take the square root of that, is going to give us V. Okay, so the kinetic energy we calculated was 5.6 times 10 to the negative 16 Newton meters. And we're going to divide that by 1/2 and by the mass, which you are given as 1.67 times 10 to the negative 27 kilograms. Okay, so again, I'm going to, in place of this Newton, I'm going to put that a Newton is a kilogram meter per second squared, and it was a Newton meter. Okay, so kilograms are going to cancel. It'll be meter squared over second squared. take the square root of that, and we'll get meters per second. So if we do all this math, what we should get is 8.2 times 10 to the 5th meters per second. So that electron, or that proton it was, placed on a positive plate will move toward the negative plate at a velocity of 5.2 times 10 to the 5th meters per second. Okay, then the last thing that we will do today then is the On Your Own 14.10. And let's look at what we are given there. So this says that capacitors are used to accelerate ions so that their behavior can be studied when they collide with other ions. A physician wants to get an ammonium ion. So the ion is 2.8 times 10 to the negative 26 kilograms. That's its mass. So this is an ammonium ion. And we are given that Q is equal to negative 1.6 times 10 to the negative 19 coulombs. And it is traveling at a speed of 1.2 times 10 to the 6 meters per second. And it's going to collide with another ion. If the capacitor, so the capacitor is 2.3 times 10 to the negative 6 farads, okay? So then we want to know what charge must the capacitor hold. So we want to know what is the charge on the capacitor, given the information that we have. Okay, so this one is going to require us to work backwards the other way, because now we can figure out the kinetic energy because we know the velocity that the ammonium ion is moving, with what velocity the ammonium ion is moving. So kinetic energy is equal to 1/2 mv squared. So 1/2 times the mass, which we were given, 2.8 times 10 to the negative 26 kilograms. And then square that, so same thing. Oh no, sorry, you don't square the mass, you square the velocity. The velocity is 1.2 times 10 to the 6 meters per second, and we're going to square that whole thing. Okay, so what you should get when you do that calculation is that you should get 2.0 times 10 to the negative 14 and what you will get is kilogram meters per second squared times meters. So you're going to get Newton meters, which is a joule. Okay, so kinetic energy is 2.0 times 10 to the negative 14 joules. Okay, so if we know that the kinetic energy is that amount, then we know that the potential energy is going to be the opposite of that. So the potential energy is going to be negative 2.0 times 10 to the negative 14 joules. Because that kinetic energy, where did the kinetic energy come from? It came from a decrease in the potential energy. Okay, so now we know the potential energy, we know the change in potential energy. So delta PE, the change in potential energy, is equal to Q times delta V. Okay, so now we can calculate delta V. So the change in potential energy divided by Q will give us delta V. Okay, we just calculated the change in potential energy as negative 2.0 times 10 to the negative 14 joules. And we were given Q as 1.6 times 10 to the negative 19 coulombs. So doing that, we will get that delta V is going to be equal to negative 1.3 times 10 to the 5 joules over coulombs, which is a volt. So a Newton meter over coulomb, that is a volt. Okay, so now we're still not there yet because we were asked to find what charge what charge needs to be stored on the capacitor. Okay, so the other equation that we have is that the electric potential is equal to the charge that is stored on the positive plate divided by the charge of the capacitor. Okay, so we're going to solve for Q here. So delta V, I'll just those will cancel. So the charge of the capacitor times the electric potential is going to equal Q. So we saw that we were given that the charge of the capacitor is 2.3 times 10 to the negative 6 coulombs per volt, or a farad, times the electric potential that we calculated. So volts are going to cancel, and we will get that Q is equal to 0.30 coulombs. So in order for this ammonium ion to move at the velocity that we were given, you would need the positive plate of the capacitor would need to store 0.30 coulombs of charge. And this also, so this would be the charge that's on the positive plate. The charge on the negative plate would just be the opposite of that. It's going to be negative 3.0 coulombs. So the two plates hold the same magnitude of charge. They're just opposite. One is positive and one is negative. Okay, so we will stop there. That covers the second part of module 14, and in a separate recording I will do the practice problems that go along with this module.